Hello my dear students. So now I am going to discuss the questions given in your textbook related to Unit 16. So that is Grade 10, Unit 16. You can remember in the lesson we discussed all the changes. Physical changes, chemical changes, then you know how chemical changes take place. We wrote the chemical reactions, then we discussed how to write balanced equations for chemical reactions. Then we discussed the types of chemical reactions. Thereafter, we discussed the reaction of metals with different substances. From there, we went on to understand the activity series. And from there, we discussed the extraction of metals, that is extraction of iron and extraction of gold. And towards the end of the lesson, we discussed the properties, preparation and the uses of different gases, hydrogen, oxygen and carbon dioxide. So I am sure you all have a very good understanding of the lesson and I am sure you have already answered all these questions given in your exercise book. If not, do them first by yourself and then you can check your answers with my discussion. So exercise, the first question. Opposite each of the following statements, place a tick if it is true and a cross if it is false. So you need to identify whether the statements are true or false. The first one, melting of wax is a chemical change. So when we say melting of wax, what happens? The solid wax turns into a liquid. So there is a physical state change only. So it is a physical change. That means this statement is wrong. Melting of wax is a chemical change. That is false. A chemical change occurs in a fireplace burning firewood. What is that? Combustion is a chemical reaction. Why? When you say firewood, it has certain substances. You all know you have discussed biomolecules, mainly the carbohydrates. Carbohydrates are made up of carbon, hydrogen and oxygen. So when we burn firewood, the products are usually carbon dioxide and water vapor. So there you can remember it is a chemical change. Combustion is a chemical change. So a chemical change occurs in a fireplace burning firewood. That is a true statement. It is true. Then the third one, evaporation of eau de cologne is a physical change. That is also correct. If you pour a little amount of eau de cologne maybe on your palm, it is a liquid and it evaporates off. So the liquid becomes the gaseous state. So there is a state change taking place. Only the rearrangement of constituent particles. So that is a physical change. The statement is true. Evaporation of eau de cologne is a physical change. Then the fourth one, rusting of iron is not a chemical change. That is also incorrect. Why? When you say iron, it is the pure metal, iron Fe, and when it undergoes rusting, it actually reacts with water or moisture as well as oxygen in air and the rust is formed. That is an oxide of iron. So the reactant is iron, water and oxygen and there is the product, that is the rust. So that is a chemical change. So rusting of iron is not a chemical change, it's a false statement. Then the fifth one, a chemical change occurs when a salt solution is made by dissolving crystals of salt in water. Is this a chemical change? Now you have the solid salt crystals, you dissolve it in water, you get the salt solution. But if you pour that salt solution into an evaporation dish or any dish for that matter, and if you let the water to evaporate off, you can get the sodium chloride crystals or the salt crystals back. So there we are just dissolving it. We are making a mixture only. There is no chemical reaction taking place. So that is not a chemical change. So this statement, a chemical change occurs when a salt solution is made by dissolving crystals of salt in water. It is not true or it is false. So those are the 5 statements given to you. Melting of wax is a chemical change. False. A chemical change occurs in a fireplace burning firewood. True. Evaporation of eau de cologne is a physical change. True. Rusting of iron is not a chemical change. That is also false. And a chemical change occurs when a salt solution is made by dissolving crystals of salt in water. That is also false. So these are the statements. I am sure you did them all correctly. With that, I will move on to the next slide, the next question. Question number 2. Identify each of the following reactions as combination, decomposition, single displacement and double displacement. So here students, normally when we use the terms for the different reactions, we call it as chemical combination reaction, chemical decomposition reaction, but you can identify it as combination and decomposition. So they want us to identify these. Now you can remember students, if we write the general equations, if A and B combine to form C, then it is a combination reaction. If A is converted to or decomposed into B and C, this is decomposition. If you have A plus BC, where it becomes AC evolving B or displacing B, then this is a single displacement. Single displacement. And if you have AB plus CD, where A combines with D and B combines with C, then of course this is a double displacement. So you have either elements or compounds, they combine together and form only one product. That is a chemical combination reaction. If you have one compound, that decomposes, separates into again compounds or elements. That is chemical decomposition or decomposition reaction. You have an element and a compound, and this element displaces another element from the compound. Then it is a single displacement reaction. You have both compounds and both the components are displaced by each other. A displaces C, B displaces D. So it becomes a double displacement reaction. So this is the basis of the 4 types of chemical reactions. Using this, you can identify the above reactions. So here we have the first one. Sodium and oxygen, 4 sodium plus 1 O2 giving rise to sodium oxide. Easily you can identify it is a chemical combination reaction. So here I will write it as combination. They have asked us to identify them as combination, decomposition, single displacement and double displacement. So first one, combination. Then 2Ag2CO3, silver carbonate. Ag is silver, silver carbonate gets converted to 4 silver plus 2 carbon dioxide and 1 oxygen gas. So one compound getting decomposed into many other substances. So that is a decomposition reaction. This is decomposition. Then the third one, zinc and sulfuric acid giving rise to zinc sulfate and H2 gas. So here you can see zinc has displaced hydrogen. That is why zinc combines with sulfate, you get zinc sulfate. Hydrogen has been displaced. So there is only one displacement, single displacement. This is single displacement. Single displacement. Then we have this one, sodium chloride and silver nitrate. NaCl, sodium chloride, AgNO3, silver nitrate, giving rise to AgCl, that is silver chloride, and sodium nitrate, NaNO3. So easily you can see that it is a double displacement reaction. Sodium combines with nitrate, silver combines with chlorine. So it is a double displacement. Double displacement. Single displacement, previous one, this is double displacement. Then the last one, sodium plus water giving rise to sodium hydroxide and H2. What is that? Now water is hydrogen and OH, H plus and OH minus, that is H2O. So from that, sodium displaces hydrogen and the OH combines with sodium. So that is also a single displacement reaction. You can remember, students, in the activity series, there is hydrogen in the middle. Sodium is at the top, highly reactive. Hydrogen is somewhere in the middle, just before copper. So therefore, you can remember, students, this is a single displacement reaction. The metal that is above can displace the metal below it in the activity series. So sodium plus water giving rise to NaOH and H2 is a single displacement reaction. So I'm sure you all can identify all these correctly. Sodium and oxygen giving sodium oxide, chemical combination or combination reaction. Silver carbonate decomposes to silver, carbon dioxide and oxygen, decomposition. Zinc and sulfuric acid giving rise to zinc sulfate and hydrogen, single displacement. Sodium chloride and silver nitrate giving rise to silver chloride and sodium nitrate, it's double displacement. Sodium and water giving rise to sodium hydroxide and hydrogen, it is a single displacement reaction. So I'm sure you all have all identified this correctly. With that, we will move on to the next question. Third one, write balanced chemical equations for the following. So it's important you have to write balanced chemical equations. The first one. So the first one, sodium and hydrochloric acid react to produce sodium chloride and hydrogen. So here, students, they have given you all the reactants as well as the products. But even if they tell you only the reactants, you should know to write the products for all the reactions that we have discussed so far. So you should remember those. Then you can balance the reaction. So here it is sodium and hydrochloric acid, HCl. So symbol of element, chemical formula or molecular formula for the compounds. They react to form sodium chloride and give rise to H2 gas, hydrogen gas. So again, by looking at the reaction, you can immediately identify it as a single displacement reaction also. We don't have to do that for the question. We need to balance it. Look at the reaction, students. Sodium, correct. HCl, one hydrogen, one chlorine. But here you have one chlorine but two hydrogens. So that has to be balanced. We need to put the coefficient 2 here in front. Then again, chlorine becomes 2. So to balance that, we need to put 2 as the coefficient here in front of sodium chloride. Again, we need to balance sodium. So you need to put a 2 here in front of sodium. 2 sodium, 2 HCl gives rise to 2 NaCl and 1 H2. That is the balanced chemical equation for the reaction between sodium and hydrochloric acid. Is that okay? So then we will answer the next one. Lead nitrate and dilute sulfuric acid. Lead nitrate, that is PbNO3 twice. NO3 is minus, it is a radical. So, one valency, Pb has the valency 2. So, lead nitrate PbNO3 twice and sulfuric acid. H2SO4, dilute sulfuric acid, react forming lead sulfate and nitric acid. So, they react and form lead sulfate and nitric acid HNO3. PbNO3 twice plus H2SO4 give rise to PbSO4. There both the valencies are 2, so PbSO4 and nitric acid HNO3. Check the number of atoms. PB1 okay, but NO3 there are 2 molecules. So, there also we need to have 2 molecules. This is the observation method, students. So, you can observe and answer. You can see the components have not really changed. It's just the double displacement. So, we need 2 nitrate and here also we have 2 H2 but there is only 1 hydrogen. So, we need to put a coefficient 2 there, 2 HNO3, but sulfate is also balanced. So, 1 PbNO3 lead nitrate with 1 sulfuric acid giving rise to 1 lead sulfate and 2 HNO3, that is nitric acid. So, that is the balanced chemical equation. With that, we will move on to the next slide. The third one. Calcium reacts with water giving calcium hydroxide and hydrogen gas. Calcium reacts with water. So, this is also a reaction, students, that we did not do in the lab. Even the sodium with acid, calcium with water, because we know they are very reactive. The reactions are usually violent. So, we did not try it out in the lab. Calcium reacts with water giving rise to calcium hydroxide, CaOH twice and H2 gas, hydrogen gas. So, calcium and water giving rise to calcium hydroxide and H2. How are we supposed to balance it? Calcium, it's correct, it's balanced. But here you can see there is only 2 hydrogen atoms and 1 oxygen atom. But here you can see there are 2 oxygen atoms and 2 plus 2, 4 hydrogen atoms. So, to balance that, we need to put a coefficient 2 here. So, 2 into 2, 4 hydrogens, 2 plus 2, 4 hydrogens. It's balanced. 2 oxygen, here also it's 2 oxygen. So, calcium plus 2 water gives rise to calcium hydroxide plus hydrogen gas. So, that is the balanced chemical equation. Then the fourth one. Aluminium and dilute hydrochloric acid react giving aluminium chloride and hydrogen. We have come across reactions like these. So, aluminium plus hydrochloric acid gives rise to aluminium chloride, AlCl3 plus H2 gas, hydrogen gas. How do we balance this? Now, you can see chlorine 1, chlorine 3. Hydrogen 1, hydrogen 2. So, you are familiar with that. When we have 2 and 3, you need to consider the least common multiple. That is 6. So, we need to get 6 there. So, what can we do? We can put a 2 in front here, 2 AlCl3. Then, we need to have 3 H2. So, you have 2 into 3, 6 chlorines as well as 3 into 2, 6 hydrogen atoms. So, to balance that, we put a 6 in front of HCl. So, we have 6 hydrogen, 6 chlorines. Then, we need to balance aluminium. There should be 2 aluminium atoms. So, 2 Al plus 6 HCl gives rise to 2 AlCl3 and 3 H2. So, that is the balanced chemical equation for the reaction of aluminium with dilute hydrochloric acid giving rise to aluminium chloride and hydrogen gas. Then we'll move on to the last question of this main question, that is sodium carbonate reacts with dilute hydrochloric acid forming sodium chloride, water and carbon dioxide. So we have sodium carbonate, Na2CO3 plus dilute hydrochloric acid, HCl, giving rise to sodium chloride, NaCl, plus water and carbon dioxide. So when we write, always when we have space in front of each component, then it is easy to balance it. So sodium carbonate, Na2CO3, and here we have HCl, it has not been balanced. So you can see 2 sodium, there is only 1 sodium. Then we will have to put a 2 in front of sodium chloride. So if we do that, now you can see sodium is balanced but chlorine is not balanced. So 2 chlorines, if we want to balance that, we need to put a 2 in front here. So this becomes 2 HCl. Now check the number of hydrogens. 2 hydrogen atoms, there are 2 hydrogen atoms. That is balanced. Now look at carbon and oxygen. We have 1 CO3. So there is only 1 carbon. Here you can see there is only 1 carbon there. You need to count the number of oxygen atoms. There are 3 oxygen atoms here. There is 1 oxygen and 2 oxygen atoms there. So that is also 3 oxygen atoms. So it is balanced. You can see 1 sodium carbonate with 2 HCl gives rise to 2 NaCl, 1 water and 1 carbon dioxide. So that is the balanced chemical equation. I am sure students, you were also able to write all these balanced equations correctly. So with that, I will move on to the next slide. Question number 4. Answer the following questions that are based on the metals given below. So here they have given us some of the metals: calcium, magnesium, copper, zinc, aluminium and iron. So I am sure now you are familiar with all the symbols that of the metals present in the activity series. So calcium, magnesium, copper, zinc, aluminium and iron. The first question, what is the metal that reacts fastest with water? Fastest with water. So here you can see calcium, magnesium, copper, zinc, aluminium and iron. Now we only use the reaction of magnesium with water. There also magnesium doesn't react with cool water. It reacts with hot water and with steam. But sodium, you can remember, it is a violent reaction or a very fast reaction. We did not do the reaction of calcium with water, but in the activity series, if you remember students, potassium, sodium, calcium, magnesium. So potassium, sodium and calcium are more reactive than magnesium. Although we didn't try the reaction, calcium is more reactive than magnesium. But all these, copper, zinc, aluminium, iron, mostly copper, zinc and iron, they are not that reactive. They are all moderately reactive. Even aluminium, it doesn't react very fast. It can react but at stronger conditions. So the question is, what is the metal that reacts fastest with water? So that is going to be calcium. If we write the symbol is fine. If you want, you can write the name also. That is up to you all. Since the standard symbols are given, you can just stick to that. Calcium reacts fastest with water. Then the second one. What is the metal that does not react? So here, does not react with dilute hydrochloric acid. Now that again, you can remember the activity, students. We use the dilute hydrochloric acid, we put different metals into it. There also, we did not use calcium. Because if you remember, I said it is there in your book also. Metals like sodium, calcium, potassium, they react violently with acids. Even if the acids are dilute, they react violently. So, we don't try those reactions in the laboratory. So, calcium reacts with dilute HCl, hydrochloric acid. Magnesium, yes, when you put magnesium into it, it does react with dilute hydrochloric acid. How about copper? When we did the activity, you can remember there was no change when we put a piece of copper into dilute hydrochloric acid. So, it does not react with dilute HCl. Zinc, yes, the bubbling was fast, evolving of liberation of gas, hydrogen gas was fast. Something similar to magnesium. That was also a fast reaction. Aluminium, that also reacted quickly with dilute hydrochloric acid. So, magnesium, zinc and aluminium, they react fast with dilute hydrochloric acid. Copper did not react. Iron, what happened there? When we put iron, it took a long time. It is a very slow reaction, but it does react with dilute hydrochloric acid. So, the question is, what is the metal that does not react with dilute hydrochloric acid? So, that is copper. Answer is copper. So, I am sure you all can understand this and you would have answered them correctly. Look at the question carefully. The first one, metal that reacts fastest with water, that is calcium, and the metal that does not react with hydrochloric acid, that is dilute hydrochloric acid, is copper. So, then we will move on to the next part. Again, the same question, answer the following questions that are based on the metals given below: calcium, magnesium, copper, zinc, aluminium and iron. So, the third part of the question, which metal effervesces fastest with dilute hydrochloric acid? You know the meaning of effervesces. Liberates a gas. You see the bubbling because the gas is liberated during the reaction. Effervesces fastest with dilute hydrochloric acid. So, we already discussed. I told you all we don't try calcium because it's very violent. So, what do you all think? It will be the metal that evolves hydrogen very fast or effervesces fastest with dilute hydrochloric acid. But we did the reaction of magnesium, copper, zinc, aluminium and iron. Magnesium, zinc and aluminium are fast reactions. Iron is a slow reaction. Copper does not react. So, the question is, which metal effervesces fastest with dilute hydrochloric acid? According to the reactivity, it has to be calcium. But here I will say it is a very violent reaction. Very violent reaction. So, normally we don't do that in the lab. But out of all the reactions that we did, it is magnesium that effervesces fast. So, here we can say, I'll say reactions carried out in the lab magnesium effervesces fast. So, this is for your additional knowledge, students. You have seen this, you have learned this before, but you have to remember, if it is just the order, normally it will be calcium. But since it's a violent reaction, we did not do that in the lab. So, we only use the rest of the metals. Out of those, we saw that magnesium reacts very fast with dilute hydrochloric acid. So, here the answer is going to be calcium. Theoretically and according to the reactivity of calcium, that reacts fastest with dilute hydrochloric acid. Therefore, it effervesces fastest with dilute hydrochloric acid. Then the fourth one, what is the metal that tarnishes fastest when exposed to air. Now again, out of all these metals, what do we write there? If we say the metal that tarnishes fastest when exposed to air, again it is going to be calcium. Why? Calcium is at the top of the activity series. Potassium, sodium, calcium, then only magnesium. Now when we have magnesium, we keep it in the lab. It does react with oxygen in air. That is why it tarnishes. You get the oxide layer forming over it. We need to clean it before we use it for activities. But still, it takes a longer time. All the other elements, even aluminium tarnishes. The vessels, aluminium vessels that you have at home, you will see initially when you buy it, it will be very shiny. But when you use it over a longer period of time, you see the color tarnishing. The shine is lost. So, there aluminium also tarnishes. But copper, zinc and iron, usually they take a very long time. Their reactivity is moderate. So, they don't tarnish quickly. What is the metal that tarnishes fastest when exposed to air? That is going to be calcium. So here again calcium. Now here students, which metal effervesces fastest with dilute hydrochloric acid? So I told you all theoretically according to the activity series it has to be calcium. But out of the metals that were tried out in the lab, the activity that we carried out in the lab, we don't use calcium because it's a very violent reaction. So there it has to be magnesium. The same way, if we look at all the metals, according to their reactivity also, calcium is the metal that will tarnish fast. We tried with sodium. You can remember that. Sodium, as we cut a freshly cut piece of sodium, if we keep it exposed to air, when you look at it itself, it tarnishes. Similar to that, even calcium can tarnish quickly. You all have to remember that. So with that, I'll move on to the last part of this question. The fourth one, answer the following questions that are based on the metals given below. The same thing, calcium, magnesium, copper, zinc, aluminium and iron. So the fifth part of the question, what are the metals that would not react if put into a copper sulfate solution? So here students, if you all can remember the activity series, anyway you are supposed to remember it. It is potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, then it is zinc. So if we consider the order of the activity series, I will write it here. So we have potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, then we have hydrogen in the middle. After that, we have copper. After copper, if you can remember, we have mercury, then we have silver, platinum and gold. So that is the order of the activity series. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, platinum and gold. Now, if you look at this question, students, what are the metals that would not react if put into a copper sulfate solution? You all know any metal that is above copper in the activity series will displace copper from its metal ion solution or the metal salt solution. So, copper sulfate is the copper salt solution if we put all these metals. Now, calcium is here, magnesium is here, aluminium, zinc, iron. All these are above copper. So, they all will displace copper from the solution. So, the question says, would not react. So, if it is would not react, that means there is no metal. We might have to say none of the above. None of the above metals. So if the question had been, what are the metals that would react? Then of course, all the metals except copper. All of them can displace copper from the metal salt solution. Is that clear to you all? Always the metal that is above in the activity series will displace the metal from its salt solution because it is more reactive. So all of them can displace iron. So according to the question, there are no metals given there that cannot react if put into a copper sulfate solution. Is that clear to you all? Then the sixth one. What are the metals that burn easily with a flame forming the oxide? What are the metals that burn easily with a flame forming the oxide? What are the metals that burn easily? You can remember we did the activity with magnesium. When we burn magnesium in the Bunsen flame, it burns with a bright white flame forming magnesium oxide. So that is one. Then if you consider the reactions. Now calcium, we don't have to burn it. Like sodium, potassium, they are highly reactive. So we don't do that. How about copper? Copper, if we heat it for a long period of time, just the color tarnishes. But if you heat it strongly, under very strong conditions only, the copper oxide will be formed. Same goes for zinc and iron. They are also not that reactive, so you need to heat them for a very long period of time, and there should be strong heating if they need to form the oxide. So here students, if we consider aluminium, even you can remember we use aluminium foil in the households. So there we use it for a long period of time. Sometimes we use it to wrap food that is very warm also. Sometimes it is used for baking in the ovens. So there it does not react very quickly. So only metal, although they have said what are the metals, it is only magnesium that can burn with a flame forming the oxide. And magnesium, you can remember, it burns with a bright white flame. So that is like a specific observation. If something burns with a bright white flame, if it is a metal, then you know it has to be magnesium. So those are the answers for these questions, students. So I am sure you were also able to come to these answers, and if not, you all understood how we get these answers. So with that, I will move on to the next question. Question number 5. Explain the following scientifically. So there are some observations given to you all or statements. You need to explain them scientifically. And here explain the following scientifically. First one. Metals like sodium and potassium are stored in kerosene or liquid paraffin. Again students, if you can remember, based on the activity series, we identify the methods of storage or precautions that need to be taken when metals are stored. So there, if you remember, potassium, sodium, calcium, magnesium. Those are the metals, those are at the top of the activity series. And there are also magnesium is available in the lab as strips. We just keep them, store them inside a box, or you can even keep it in a bag. You can just keep it exposed to air. It does react, it does tarnish, there is oxide layer formed, but still you can scrape off that oxide layer and you can use the magnesium. But if you take the metals like sodium and potassium, both of them, we did the activity with sodium. You take the sodium out, you cut it, you expose the freshly cut piece of sodium to air. As you are looking at it itself, it starts reacting. And after some time, all the sodium reacts with oxygen and you get only sodium oxide. So it is a very, very fast reaction. Potassium is even more reactive. Potassium, sodium. So both these metals are highly reactive. So we need to store them so that they are not exposed to oxygen in air. So when you put them into either kerosene or paraffin, paraffin is wax, we use the liquid paraffin there. So you put them into kerosene or liquid paraffin, you cut the contact of these metals with oxygen in air. So there is no contact with oxygen and these metals. Because of that, they do not react. So that is why they have to be stored in kerosene or liquid paraffin. You have to explain that. So we can say sodium and potassium are highly reactive metals. They react very fast with oxygen in air. So by storing them in kerosene or liquid paraffin, we can prevent the contact of metal with oxygen in air. Therefore, they can be stored as metals for a long time. You all are familiar with that also, students. These metals are not available as metals in nature. They are only there as compounds. Sodium is usually found in the form of sodium chloride. Like that, even potassium, we only get compounds in nature, not the metal, because of their high reactivity. So that is what you need to write here. Sodium and potassium are highly reactive metals. They react very fast with oxygen in air. So by storing them in kerosene or liquid paraffin, we can prevent the contact of metal with oxygen in air. Therefore, they can be stored as metals for a long time, that is in the laboratory or anywhere. And also you can remember, when we store them, we usually use a dark brown color glass bottle so that light does not penetrate that much into it, or else it is a plastic bottle where light cannot penetrate. So that is also another precaution taken when storing these metals. But the main thing is you have to have them inside kerosene or liquid paraffin so that there is no contact between the metal and oxygen in air for both sodium and potassium. So with that, students, I'll move on to the next part. Fifth question, again explain the following scientifically. Copper metal has been in use from ancient times. So as you know, students, we use many metals in our day-to-day life. Some of the metals have been in use for the recent years. But some metals like gold, copper, iron, they have been in use from ancient times. So here the question is about copper metal. Copper metal has been in use from ancient times. How can you explain that? Now again, if you think of the activity series, copper is after hydrogen in the activity series. So it has a moderate reactivity. It exists as compounds in nature, compounds of copper. in the natural environment, that is the O, how do you separate the copper metal? Like iron, we use a reducing agent or a reductant. You are familiar with those terms. Reducing agent or a reductant is used to separate the copper metal from its ore. Like the blast furnace method used for extraction of iron, we can use a method to extract copper from its ore. That is also a somewhat easy method. Like extraction of iron, you can extract copper easily. So one thing, you have the O, that is the copper compounds are present as O's in nature, and you can easily separate out copper, or you can extract copper from the O's using a reducing agent. Once you get the copper metal, now we saw the reactions. Copper doesn't react easily with oxygen. You have to heat it for a long time, and it has to be strong heating. And also copper doesn't react with water. Copper doesn't react with dilute acids. So that means the reactivities of copper is also very less. So because of that, we can make lot of objects from copper and use that in our day-to-day life. Because copper does not react with oxygen, water, that is cool water, or even hot water or steam, and also it doesn't react with oxygen that quickly. So because of that, it is very, very useful, and that is why it has been in use from ancient times. So you have to list out all the reasons. So here we can say copper, I will use the symbol, exist as compounds, that is in O's in nature. It can be extracted using a reductant or reducing agent because it is a moderately reactive metal. So similar to iron, we can also extract it using a reductant or a reducing agent. And you can say, since the metal is moderately reactive and it does not react with oxygen, water, and dilute acids very easily. Therefore, objects made with copper can be used for a longer period of time. So because of that, it is easy to use copper. So since it is a metal that is moderately reactive and it does not react with oxygen, water and dilute acids very easily. So it has to be easily there EA. Right. So it does not react easily. Therefore, objects made with copper can be used for a longer period of time. So, in addition to these, students, you all have to remember like iron. Now, when we mix iron with other substances, we get the alloys of iron. Similar to that, we can make alloys of copper. A common alloy that you all are familiar with is brass. When copper is mixed with zinc, we get brass. And you know, we make a lot of objects using brass, and it has been in use over a long period of time. So that is also possible. That is another reason again why we use objects made up of copper and why it has been in use for a long period of time. So that also can be included here. Copper can be used to make alloys like brass, that is copper and zinc. This is also not very reactive. So there are many reasons why we use copper. So if we go back and go through the answer again, copper metal has been in use from ancient times. The reasons: copper exists as compounds, that is in ores in nature. It can be extracted using a reductant or a reducing agent because it is a moderately reactive metal. And also, since the metal is moderately reactive and it does not react with oxygen, there is oxygen, water and dilute acids very easily. Therefore, objects made with copper can be used for a longer period of time. And as I discussed before, you can see it can be used for a longer period of time, and also copper can be used to make alloys like brass. So there we mix copper and zinc. So that is also not very reactive. So because of that, either copper metal can be used directly to make objects, or we can make alloys and make objects using those alloys. Either way, because of its low reactivity, it can be used for a very long period of time, and that is why it is very useful to us. So with that, students, I will move on to the next part of the question. So question number 5, the third part of the question. So here, as I told you, students, explain the followings. It should be following scientifically. Then the third one, special methods are not essential to prevent tarnishing of objects made of aluminium. So you can remember, students, we have discussed these processes. Now there is the process of corrosion, there is the process of tarnishing. Now what is tarnishing? Normally you all see in the lab we have magnesium strips. So when you take the magnesium strip, it's very shiny. But with time, the color, the shine of magnesium is lost. That is known as tarnishing. That occurs over a long period of time. Now you have seen sodium. We took a freshly cut piece of sodium. You look at the freshly cut surface, it's very shiny. But within minutes, that shine will be lost. So there sodium tarnishes very quickly. Now here we are worried about aluminium, or we consider the metal aluminium. At home, in the households, you have seen many objects made up of aluminium. Now that is also whitish color, silvery shiny metal. Now it has a nice shine. If you keep it for a very long period, the shine can be lost to a certain extent. So there, now although the question says we don't need to prevent tarnishing, you can see a certain amount of tarnishing of aluminium if only pure aluminium is taken. But most of the objects that we use at home, they are not just aluminium metal. There are some alloys of aluminium. Where you know alloys, another metal or another element is mixed with the metal aluminium. So that is an alloy of aluminium. This particular alloy of aluminium does not tarnish. So that is why usually for years the shine of aluminium is not lost. But at the same time, as I told you all before students, if you have the pure aluminium metal like magnesium, now this is what happens. You have the aluminium metal and this does react with oxygen. When aluminium reacts with oxygen, there is aluminium oxide formed, Al2O3. So if you are to balance the equation, you all know we need to have 3 oxygen and 4 aluminium. But this aluminium oxide layer forms a thin layer over aluminium. So there will be a very thin layer of aluminium oxide over this aluminium metal. And that protects the aluminium from further reaction. So when this aluminium oxide forms, the shine will be reduced or lost to a certain extent. So that is what we call as tarnishing. So here when this forms, there will be tarnishing of aluminium, but further reaction with oxygen will be prevented. Now reaction with oxygen of metals is what we call as corrosion. So further corrosion of aluminium will be prevented. There will be slight tarnishing if it is pure aluminium, and there the aluminium oxide will form over the aluminium metal. That prevents further corrosion of aluminium with oxygen. That is what you have to remember, students. So this particular aluminium oxide prevents the corrosion of aluminium with oxygen any further. So like magnesium, this is also protected. But you can remember, students, whenever we use magnesium strip in the lab, what do? We take a sandpaper and we scrape off the magnesium oxide layer. So you get the shiny magnesium, we use it for reactions. But in the case of aluminium, it is a very thin layer, and especially when it is a household utensil, we don't need to scrape it off. We just use it as it is. So can you all understand that? You have to remember, students, the difference between corrosion and tarnishing. Although in this question it says tarnishing. Tarnishing means the shine is lost. You have learned that before. Shine of the metal, the lustrous nature of metal is lost due to the reaction of metals with atmospheric air or other materials, usually atmospheric air. But when we say corrosion, that is the reaction of metal with oxygen. So during corrosion, there will be tarnishing of metal. But here, once the tarnishing happens, a very thin layer of aluminium is formed, and that prevents further corrosion of the metal with oxygen. So because of that, we don't need to take any preventive measures to prevent the corrosion of aluminium with oxygen. Even if the shine is lost to a certain extent, even if it tarnishes to a certain extent, that does not matter much, because still the quality of aluminium will be retained. Is that clear to you all? So to answer this question, special methods are not essential to prevent tarnishing of objects made of aluminium. So to answer that, we can say aluminium reacts with oxygen in air and forms aluminium oxide, that is Al2O3. This forms a thin protective layer over the aluminium metal. So we can say due to this, there will be a decrease in the shine of aluminium metal. So that means there will be a small amount of tarnishing. But further corrosion of aluminium is prevented by the oxide layer. That is one point that I discussed with you. The other point, usually the objects used in day-to-day life are made of alloys of aluminium. This does not tarnish. So when we say does not tarnish, it will not corrode also. So does not corrode very easily. So because of these two reasons, therefore, we do not need to take measures to prevent the corrosion. So in that sense, we can say according to the question, tarnish of the metal, aluminium. So can you all understand that, students? According to the question, if we go back, you can see here they have asked special methods are not essential to prevent tarnishing. So as you know, tarnishing is the loss of shine, but that can occur because the aluminium oxide layer forms. It is a protective layer. Because of that, further corrosion is prevented. So we don't need to take special methods to prevent corrosion because aluminium is protected by the aluminium oxide layer. That is what you have to remember, students. So you need to know the difference between this tarnishing and corrosion. Is that clear to you? So that is how we answer this question. Aluminium reacts with oxygen in air and forms aluminium oxide, that is Al2O3. This forms a thin protective layer over the aluminium metal. Due to this, there will be a decrease in the shine of aluminium metal. So, there will be a certain amount of tarnishing. But further corrosion of aluminium is prevented by the oxide layer. That is one. Then the other thing, this is again for your knowledge, students. Usually, the objects used in our day-to-day life are made of alloys of aluminium. This does not tarnish. So, that is why if you have seen objects made up of aluminium at home, you might think, okay, this shine does never tarnish. It is always shiny because it is an alloy of aluminium. So, they do not corrode very easily. So, that is why, therefore, we do not need to take measures to prevent the corrosion, that is tarnish of the metal aluminium. Is that clear to you all, students? So, then we will move on to the next question. Explain the following scientifically. So, this is again explain it scientifically. The fourth one, metals like sodium and potassium have the shortest history of usage. Why shortest history of usage? Because they are highly reactive. Potassium, sodium, the first two elements of the activity series. Highest reactivity. So, because of that, they don't exist as metals in nature. They only exist as compounds in nature, and that also sodium is mainly present in seawater as sodium chloride. So, recently only they were able to use the method of electrolysis. You can remember, for the highly reactive metals, we need to go for the method of electrolysis. One thing, it is expensive, and also that technique was developed very recently. So, that is why only when they were able to extract sodium and potassium only we started using them. And the other thing, because they are highly reactive, we already discussed in the same question, we need to take protective measures to store them. So, because of that also, both these metals were not in use for a long time. They have the shortest history of usage, mainly because of their high reactivity. Their existence was not known, it was difficult to separate them, and also it is difficult to store them. So, those are the reasons why they have the shortest history of usage. So, we need to answer that, sodium and potassium. So, here we can say both sodium and potassium are highly reactive. They do not exist as native metals, but they exist as compounds in nature. To extract the metal from the compound, methods like electrolysis has to be used. This technique was developed not very long ago. Also, because of the high reactivity, precautions need to be taken when storing these metals. Thus, the metals sodium and potassium have the shortest history of usage. So you have to remember, students, they are highly reactive, so they are not available as native metals, and it is difficult to extract these metals from their compounds. You need to use methods like electrolysis, and that was developed also somewhat recently, and it is difficult to store these metals. So because of all these reasons, the use of these metals have been the shortest history. So they have the shortest history of usage. Sodium and potassium have the shortest history of usage. So that is the answer to this question. If I go back, again you can see both sodium and potassium are highly reactive. They do not exist as native metals, but they exist as compounds in nature. To extract the metal from the compound, methods like electrolysis has to be used. This technique was developed not very long ago. Also, because of the high reactivity, precautions need to be taken when storing these metals. Thus, the metals sodium and potassium have the shortest history of usage. So, I am sure you were able to answer this, explain this scientifically. With that, I will move on to the last part of this question. Explain the following. Explain the following scientifically. When zinc is added to a copper sulfate solution, copper is precipitated. But when copper is added to zinc sulfate solution, zinc is not precipitated. You can remember that. We did this activity. You have a solution of copper sulfate. You put a piece of zinc into that. You will get copper precipitating. But if you have a solution of zinc sulfate, and if you put a piece of copper into that, there is no reaction. What is the reason? Again, related to the activity series. If you can remember the order of metals, potassium, sodium, calcium, magnesium, aluminium, zinc, iron. So, if I write those metals, we have zinc, iron, then we have tin, lead, hydrogen, then we have copper. So, according to this order, zinc is above, copper is below. Only the metal that is above another metal can displace the second metal from its salt solution. So, here copper sulfate is the salt solution of copper, and zinc is above copper in the activity series. So, zinc can displace copper from its salt solution. But if you take this, it is the other way around. Copper is below zinc in the activity series. So, because of that, copper will not displace zinc from its salt solution. The reason being, copper is less reactive than zinc. So, that is how the displacement reaction occurs. That is what you need to explain here as well. So, here, we can say zinc is above copper in the activity series. That is, zinc is more reactive than copper. Therefore, zinc can displace copper from its salt solution, but copper cannot displace zinc from its salt solution. So, zinc can displace copper from its salt solution, but copper cannot displace zinc from its salt solution. That is why copper is precipitated when you put a piece of zinc into copper sulfate. But if you put a piece of copper into zinc sulfate, there is no reaction. So, let's look at the question. When zinc is added to copper sulfate solution, copper is precipitated. But when copper is added to zinc sulfate solution, zinc is not precipitated. So, this is the explanation. Zinc is above copper in the activity series. That is, zinc is more reactive than copper. Therefore, zinc can displace copper from its salt solution, but copper cannot displace zinc from its salt solution. So, you can complete the answer by saying that is why copper is precipitated when zinc is added to copper sulfate solution, but zinc is not precipitated when copper is added to zinc sulfate solution. Zinc sulfate solution. So, this is to complete the answer. So, you can say that is why copper is precipitated when zinc is added to copper sulfate solution, but zinc is not precipitated when copper is added to zinc sulfate solution. So, I am sure students, you all also gave a similar explanation. So, you have to mention the reactivity of the metals. You can tell about the order of the activity series, and because zinc is above copper in the activity series, that means zinc is more reactive than copper. So, that is how the displacement reaction takes place. So, with that students, I will end this chapter where we have discussed the 5 questions given in the exercise of your textbook. But there are some more questions. I will discuss those in the next chapter.